Oh man, I had something I was going to tell calculus 2 today, and I just remembered it. Oh well, maybe tomorrow. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students, for the time we have just to work a little bit more on abstract algebra. Just pray that you'd bring understanding to our discussion, Lord. In your name I pray. Amen. So just to, let me just get something out of my system real quick, and then I'll answer your questions. So we talked about, for a permutation, right, which is what? It's a bijection on the set of n numbers to the set of n numbers, right? And then we talked about the set, which is moved by sigma, right? So this is what? This is just a j in n sub n such that what? Sigma of j is what? Not equal to j, right? So if the permutation permutes j, it's in the set moved by sigma. And he had like a little lemma I just wanted to prove, because I thought about it some. I think this lemma actually, it might even be a little bit helpful towards calculations. Like it gives you some kind of intuition a little bit about calculations. So, you know, this is lemma on page 57. He says if k is in the set moved by, so here's his lemma. If k is in m sigma, then sigma k is in m sigma, right? Again, that sigma k is sigma of k. So what's the proof? Proof, let's see here. He says, suppose otherwise. Suppose sigma k is fixed by, suppose there's a contradiction, right? Suppose that sigma of k is equal to k, right? I'm sorry, that's not what I'm supposed to suppose. What am I supposed to suppose? Long day. What, that's not it. What if sigma of k is in this set moved by sigma, what would that say? It would say sigma of sigma k, right? Let me put some parentheses in here, it's driving me nuts. Is equal to sigma of k, right? But sigma is a bijection, right? So that says that sigma of k is equal to k by one-to-one property, right? Or just by operating inverse both sides. Oh no, therefore k is not an element of the set moved by sigma, right? It's a fixed point of sigma, which contradicts it not being a fixed point of sigma. So whatever point gets moved, the permutation of the point also gets moved. That's the lemma. And then that was useful for theorem 3, which is the theorem whose proof that was bothering me not to finish. So what was the theorem? If sigma and tau are disjoint. And the reason I'm talking about this is because, like most of the examples I want to share with you guys today involve this theorem one way or another. If sigma and tau are disjoint, then, they commute. So what does it mean for the permutations to be disjoint? It means the set moved by sigma intersect the set moved by tau is what? Do you guys say empty? Okay. So I drew a picture and I gave you the proof of just one of the cases, right? So if you think about, so here I'm drawing a picture of all numbers from 1 to n, right? Somewhere in here there's the set which are moved by sigma. Somewhere in here there's the set which are moved by tau, right? And here, unmoved by either, right? So in other words, these, if I take x in here, x is fixed. by both tau and sigma. In other words, tau of x equals to x, and sigma of x equals to x. Them's your three cases, right? So the proof that these permutations commute is just done case-wise. So let's pick K. Let K be an element of the set moved by sigma, and consider sigma tau acting on K. What can we say? What does tau do to K?
It's fixed.
It's fixed, right? So tau of K is? Right. So that works out to sigma of K. But let's see here then, what can we say? I'm trying to remember. How do I change that to oh, but that's equal to what? You guys tell me why this next step makes sense. Tau of sigma of K. Why do I get to say that? Right, but sigma of K is what? This is an element of the set moved, right? This is the lemma. That's an element of the set moved by sigma, right? Which means it's fixed by tau. So tau of this is equal to this again. But then we have that sigma tau equals tau sigma for all such K, right? Let's use the terminology on M sub sigma. If we pick J in the set moved by tau, the argument is entirely analogous, right? So like I don't know, let's say sigma tau of J. So I'm looking at sigma of tau of J. But tau of J is an element of what? It's, by the lemma, this is an element of the set which is moved by tau, right? So by assumption, it's fixed by sigma, which means that this is equal to, yeah, tau J. But J, what's J? J is an element of M sub tau, right? So J is fixed by sigma as well. So I can say, well, that's tau of sigma of J. So there you go. That says sigma tau is equal to tau sigma on the set moved by tau. And I proved the middle case in class, right? If it's fixed by both, then you can prove equality. So that's all three cases, and that shows you that disjoint. If we have permutations which are disjoint, then they commute. Now this is why cycle notation is so nice, right? Because example. If I have sigma is like 1, 2, let me just start out with something here. 1, 2, 3, and if I have tau is 4, 5, 6, 7, like that, right? I'm making this too complicated. Let me just erase the middle. Let me erase the middle. 4, 5, 7, 6. There, that's more interesting. I don't know. Now, I can tell you what's the set. I mean, if we write cycle notation, what's the set moved by? We can view these both as in being S in this metric group of degree 6, right? Are these disjoint? That's the beautiful thing, right? The cycle notation, you can read from it what set is moved. It's the things appearing in the cycle, right? Everything else is fixed by the cycle. I mean, that's pretty much what the notation means. It means a little bit more than that. It actually tells you how the set moves within itself, right? But, yeah. And so, apparently, 1, 2, 3, 4, 5, 7, 6 is equal to 4, 5, 7, 6 times 1, 2, 3. And if you think about the mechanics of how cycle notation works, it makes a lot of sense, right? Makes perfect sense that that's the case. So how about inverses? How about powers? How do these sort of calculations go in permutations? Like, what would the inverse, if I have sigma tau inverse, what would that be equal to? Yeah. Sock shoes, right. Sock shoes would say that that is tau inverse sigma inverse, right? Because permutations are a monoid. Fast forward to tomorrow, they're a group. Okay. But we can also switch them because here's a little lemma for you. Did you believe that? Right. Yeah, if you think of them as actually pictured cycles, then it's just going clockwise versus counterclockwise. Yeah, very good, very good. So these are also disjoint, and so they commute, right? And what are those actually? Sigma inverse is 3, 2, 1, and tau inverse is 6, I can't do math, 6, 7, 5, 4, right? Now we got to be careful. What if, show you limitations of our thinking here. What if I have sigma equals to 1, 1, 2, 4 times 5, 7, and if I have tau equals to 8, 9, there. I guess I missed a number, didn't I? Yeah, why don't I just do 8, 9, 3? There we go. So my question then is, what's sigma inverse? Now I think you got the right idea, sock shoes. So, this inverse should be 57 inverse 1, 2, 4 inverse, right? So if we have multiple cycles, we don't just write them in the same order and reverse the order. We have to take care of the sock shoes identity. And then cycle by cycle, we use the sort of wisdom of switching clockwise to counterclockwise if we look at the picture. Right? I mean, so, but this is kind of dumb. I mean, if we have AB inverse, it's just, it's BA, fine, but that's also AB. So why not just write 5, 7 again? So transposition is its own inverse. That's kind of nice. 1, 2, 4 is 4, 2, 1, right? How about order? Do you guys know what the order of an element yet? No, you don't. So this definition, if sigma to the j, let's say, is equal to epsilon, but sigma to the j minus 1 is not equal to epsilon, then sigma has order j. So the idea here is that it's the smallest integer power you can sort of exponentiate. Well, in here, exponentiation just means composition of itself with itself j-fold times. When you do that and you get the identity, that means it has order j. So for example, if we look at any transposition, right? What happens? Right? Yeah, A, so we think about it, A goes to B, but then B goes to A, so A goes to A. B, well, B goes to A, but then A goes to B, so B goes to B. A goes to A, B goes to B, everything else is fixed. Everything's fixed. It's the identity permutation, right? So, right, transposition has order 2, yeah. What if we have something like ABC? ABC. A, B, C. So yeah, it's going to be order 3. I mean, I'm going to try to explain to you why this is, right? So we just take C, right? And where does C move to? So it feeds C to here, it goes to B, right? Why did I start with C? What's wrong with me? I started with C for some reason. I guess we'll stick with that. Let me redo this. Let me start with A. It just seems right. A goes to what? B. Then in here, B gets sent to C. And then C gets sent to A. Right? If we start with B, I should really use some color coding here. Missed opportunity, right? Looking ahead. So B gets sent to, you guys just told me a second ago, C. I'll make that blue. C goes to what? A. All right, this down here, C goes to what? C goes to A, okay. And then here A goes to B. Sorry, I'm a little bit, I'm getting more OCD as I teach this year. I don't really believe in that anyway, but A goes to B. B goes to C. Oh, look, A goes to A, B goes to B, C goes to C. So a cycle of length 3 has order 3. Yeah.
So like a fun proof, the case.
Yeah, so for the nth case, I guess there's probably some kind of inductive proof that could be done or something, but I'm personally
Safe to assume from here on out.
I'm personally content to look at 2 and 3 and go, oh, okay, so that works for n. Now, that's not me being a good abstract algebra professor. It's just me being tired at whatever time it is on a Tuesday. That feels like a Monday for some reason, but yeah.
It makes sense if you're just going the next step in the cycle, and however big your cycle is, you'll end up, is however many numbers you need to go to end up back where you started.
Right. Yeah. I think there's a lot of different ways you could come to a good an intuitive understanding of why that must be. What if I asked you what would the order of this be?
Least count multiple 4 and 3.
How do you know these things?
So it's kind of a question of admission. I have to figure it out something.
Ah, that's a good answer. It's been a while since I put these missions.
It makes sense.
Right.
That's how you get from negative 1 to 1.
Yeah, okay, that's not, okay, so if sigma and tau are disjoint, right? That means they commute. Which means that in the monoid, the law of exponents, sigma tau to the A, right? Or I guess we used n, is what? Sigma to the n, tau to the n. This is because, assuming what? Sigma tau disjoint, right? So if we have disjoint cycles, then I think you're right on the money, because if we let n equal to the least common multiple of the order of sigma and the order of tau, right? Let me come up with names for those because I'm getting tired of, I don't like this. Let me call this one, I don't know, what do you want? Pac-Man and Ghost. Okay, so like sigma composed with itself Pac-Man times identity permutation, right? And tau composed with itself Ghost times identity permutation. And so n is the least common multiple of these two things, right? So what does that make? There's a formula, right? I mean, how can I say n equals what? I mean, it's a common multiple of these, right? So there's some, wait a minute, least common multiple. Oh, I'm sorry, I forget how least common multiple works. I'm an idiot. On the one hand, right, it's like, let's say,
Least common multiple of 3 and 2 is
Right. Yeah, but what that means is that there's a we're not at symbols at the moment. I don't know. I mean, whatever you want here. I guess I haven't used J in this discussion yet. So on the one hand, N is J times Pac-Man, right? But on the other hand, it's also K times Ghost. It's a common multiple. So when you calculate sigma tau to the N, you get, sigma to the N, tau to the N. But that, on the one hand, is sigma to the, J Pac-Man, and it's also tau to the K Ghost, right? Right, so then we get sigma to the Pac-Man, to the J power, tau to the Ghost, to the K power, but this is epsilon to the J, epsilon to the K, also known as the identity permutation. That's not sufficient. I mean, that's necessary to show that the order of sigma tau is n, right? But what else do you need? You also need to prove that that's the smallest n for which this happens. So to prove that a smaller n can't do it, if you suppose a smaller n could do it, that would then imply that the order of sigma and tau is less than Ghost or Pac-Man, one or the other. You sort through the details. This argument we will give carefully in another context, so I'm not going to belabor it right now. So let me work an example. How about this? Sigma equals to 1, 2, 3, 3, 5, 7, 4, 6, 2. And tau equals to 1, 2, 2, 3, 4. So what's the order of sigma tau, and what's an inverse? Well, I guess there's some different things we could do here. Like, first of all, what example am I on? Example 3-ish. So first order of business would be to rewrite these in disjoint cycle notation, right? Can we do that? Let's do that. So express sigma in disjoint. I keep forgetting the S in disjoint. What's wrong with me? Well, many things, but disjoint cycle notation. All right, so how do you do that? I personally tend to start with 1. So I'm like, okay, I'm going to start with 1. So what I do is I go up here and go, okay, where's 1 go to? It goes nowhere, right? 1 go anywhere here? Nope. It gets to here? Oh, 1 goes to 2. Great. I'm at 2. Where's 2 go to? Oh, 2 goes to 4. 4 go anywhere? Okay, so 2 went to 4. I'm at 4. Where's 4 go to? 4 goes to 6. Oh, I'm getting ahead of myself. Does 6 go anywhere? No. Now I'm to 6. Where does 6 go to? 6 goes, oh, I've done something wrong.
No.
Oh, I'm not done yet, though. I'm sorry. I keep forgetting. You got to finish what you started, right? So I go to 6. 6 goes to 2. And then 2 goes nowhere. 2 gets fed into here. 2 goes to 3. 3 goes nowhere. 3 goes to 5. 5 goes nowhere, so 3 went to 5. 5 goes nowhere. 5 goes to 7. 7 goes nowhere, so 5 went to 7. 7, nowhere. 7 went to 3. 3 went to 1. Back where we started. Game over. Yeah, really. Cool. I couldn't have. I mean, I wasn't planning on this, but yay. Hey. Let's see here. My inexperience with abstract algebra brings new excitement every day I lecture on it. I'm always finding new things. It's very exciting. I should have been working homework this summer rather than working on that silly research stuff. But I would know more. Could be more intimidating to you guys. Oh well, lost opportunities. Is there anything left out? Is that all the numbers? So there's nothing. We're working in S7, right? Or we're working in S10. Who can say? Maybe it's S100. You know?
Has to be clarified.
No.
Everything not mentioned is fixed.
It depends on the context. The question.
Well, because if you
There are.
essays, then the order would be still just 7.
Right.
Fixed variable.
The order. As long as the object exists in the universe of discussion, the order is independent of the universe. It's just about the object. Yeah, that's nice.
Which is just what the moving.
Wouldn't that be disturbing? Like if you had these permutations embedded in different SNs and then behave different depending on which SN you looked at them in. You could imagine a world of math where that was the way it worked out, but thankfully that's not the world we live in. But yeah, that's it. Okay, great. So what's the order? I can't count. 1, 2, 3, 4. Oh, 7. Okay. Yeah. Oh, yeah. 1, 2, 3, 4, 5, 6, 7. Okay, yeah. I'm just used to counting. It's like, this is like you took off one finger and just yanked it off and put it on where another one was or something. It's really kind of unsettling. Tau. 1 goes to nowhere. Actually, it went to 2, right? 2 goes to 3. 3 goes nowhere. 3 goes to 4. 4 goes nowhere. 4 goes to 2, goes to 1. Yeah. This does not have to happen. It could be that when you simplify the cycles, you end up with 2 or 3, or, there doesn't have to be just one cycle after the simplification. This is a quirk of my stupid example I just made up. So, yeah. So what's the order of tau sigma? So take sigma tau to the 28, right, is equal to the sigma to the 4 to the 7th times tau to the 7th to the 4th, which is equal to epsilon epsilon. Sorry, I should have prepared a more awful example before class today, but I got involved in other things. All right, let me shut up. You guys have questions. So I hope going through this cycle calculation slowly was helpful to someone here. I could write a bunch of more stuff, but I don't think that's helpful. I think it's important to learn how to do these without writing a bunch of stuff, because writing a bunch of stuff is a surefire way to make a mistake. Right?
I think it's hard to explain what you explained about reading it right to left in book form, so it's helpful.
Yeah, I think that's true too. But again, it's a question of function composition. We're thinking of these as composition of functions. And your thought, well, they could be read the other way, is absolutely right. And there are other books which compose cycles the other way. So you gotta be careful. That other convention exists in respectable literature. Yeah.
I originally was writing them out in array format, each individual one, and then multiplying them, and that works. But
Yeah.
it's not fun.
Right. It's not a bad way. It's just
It's not fast.
exactly. How about what happens when you conjugate a permutation? Unless you guys got a question, we could do one of those. Like what happens when I take something like sigma equals to 1, 2, 4, 3, 5, and I say tau is equal to 1, 2, 3, and I calculate tau inverse sigma tau, what happens? Let's work it out. So what's tau inverse? It's 3, 2, 1, right? Sigma is what it is. And 1, 2, 3, right? So what do we get? I guess I'll start out with 1. 1 goes to 2, goes to 4, right? 4, nowhere, nowhere, goes to 1, 1 goes to 3, 3 goes to 1, goes to 2, goes to 1. Next, 2. 2 goes to 3. 3 goes to 5. Goes nowhere, goes nowhere. 5. 5, nowhere. Goes to 3. Goes nowhere. 3 goes to 2. There we go. This is not an accident. Fun fact for you. And the reason, I mean, I got some of the homeworks I've gotten from my brother who's taught abstract algebra many, many times, all right, at various levels. And this is one of the problems he puts early on because he's trying to seed students' intuition for later. The point of this calculation is not just like, well, why calculate this? I mean, right? The interesting thing here, let me not tell you what the interesting thing is here. Let's try this again for something else. Let's try this for sigma equal to 1, 2, 4, 5, and then 7, 9, 8. All right, and we'll conjugate by tau equal to 1, 2, 7. Okay, let's calculate it again. Tau inverse, sigma tau. So tau inverse, easy peasy, 7, 2, 1. Sigma is what it is. And tau is 1, 2, 7. All right. I'll start with 1 because I'm a creature of habit. That is not written in stone. It's just my prerogative. 1 goes to 2. Goes nowhere. 2 goes to 4. 4 goes nowhere. 2 goes to 4. 1 goes to 4. 4 goes nowhere. Goes nowhere. 4 goes to 5. Goes nowhere. 5. 5 goes nowhere. Goes nowhere. 5 goes to 1. 1 goes to 7. 7. 7 goes to 1. Goes nowhere. 1 goes to 2. 2 goes to 1. Full circle. Because 7 went back to 1 again. All right. Then you just got to pick something else that's not in here. 2. That seems like the only possible correct choice. Very good. So, joking. 2 goes to 7. 7 goes to 9. 9 goes nowhere. 9 goes nowhere. Where's 9 go? 9 goes nowhere. 9 goes to 8. Goes nowhere. Goes nowhere. 8. Where's 8 go? 8 goes nowhere. 8 goes to 7. 7 goes nowhere. 7 goes to 2. Oh, full cycle. Can you tell me the pattern? What does conjugation do? I mean, certainly the set of points which are moved changes before and after the conjugation, right? Like the pot of numbers which is moved amongst itself is 1, 2, and 4, right? And down here, 1 moves to 4, moves to 3, right? And 2 and 5 are on their lonesome. Up here, 3 and 5 are on their lonesome by this permutation. So before and after, the set which is moved is different, right? And down here again, 1, 2, 4, 5 versus 1, 4, 5, 7, 7, 9, 8, 2, 9, 8, right? So if you're thinking of this as a high school and you conjugate, like it's the cliques they're not the same before and after, right? Like, there's a different set of cool girls and a different set of AV guys or AV geeks or whatever. I mean, you've been in high school. I was homeschooled. I just speak from my experience in popular culture. I've been taught about these cliques that exist in high school, apparently. I don't know. But what this would seem to say is that if you conjugate the set of cliques in a high school, well, the number of students in each clique stays the same. So in other words, like the size of the sets which are moved, it's the same before and after, right? This is called cycle type. So the cycle type of sigma, it's like it's what is it made up of? It's made up of a disjoint 4 cycle and 3 cycle. And after you conjugate, you still got a disjoint 4 cycle and 3 cycle. And likewise up here, disjoint 3 cycle times 2 cycle, still disjoint 3 cycle times 2 cycle. So the cycle type is invariant under conjugation. This turns out to have interesting implications later, after you think other thoughts. For now, it's just an interesting exercise in cycle notation. I think it's actually a pretty good exercise in cycle notation, right? There's a lot here. You guys have questions? You can interrupt me at any point, you know.
I could ask a question about something training.
I make no guarantees.
This one looks like really long. I'm just wondering if not necessarily need to do it, but just it's 0.3, 0.3 to 14. My question is, you just have to, it's got A, B, and C, and it says show that these conditions are equivalent. Show A implies B, B implies C, A implies C. Show those are
I was looking for 0.4, number 14. It was hard.
0.3.
0.3, number 14, yes. This is training, or this is... Okay. Training I can do.
Yeah, I don't know if
Yeah.
it
I don't mind.
seems very long.
Maybe not. So, did I already do it in here?
No, I don't think so.
Think so. Okay. I have to ask that because I don't remember. So you guys, I can erase this, right? Yeah. Let's see here, number 14. So we're supposed to show the following conditions are equivalent for a mapping alpha from A to B where A and B are non-empty. So we have A, B, non-empty, alpha, a mapping from A to B. Allegedly, the following are equivalent. Now this is 0.3, number 14. Okay, one of the exercises I assigned you guys for training. Sorry if that sounds insulting. I just watched too much Naruto. Let's see here. So A, alpha is 1 to 1. What's B? There exists beta. Beta alpha is equal to, what is it? Did I, 1A? No, and he told us, I mean, of course, beta is where? From B to A, right? Okay. That was in the statement, I just muddled it, sorry. C, if C is from C to A and delta is from C to A, idiot. What did I just say? If gamma, right, from C to A and delta from C to A have what? Alpha gamma equals to alpha gamma equals alpha delta, then gamma equal delta. Did I just get that back? I should just pick up the book. I'm an idiot. It's alpha gamma equal alpha delta. Yeah. Then gamma equals to delta. All right. So to show the following are equivalent, I think what I would go with here, I mean, there's various logical choices, but the laziest one I can think of, if it works, is A implies B, implies C, implies A, right? If you can show that this, so to speak, is equivalent to A if and only if B, if and only if C, right? If you can understand my scribblings. So, all right. So let's start out with A implies B. So assume alpha is 1 to 1, right? Then we need to construct beta such that beta alpha is equal to 1A, right? So if alpha of A is equal to B, right? Then we're done. I mean, you could give a more lengthy solution, but I'm just going to kind of piggyback off something else here. But if alpha is equal to B, then alpha is a bijection, right? Because it's 1 to 1 and onto, if that's the case. Consequently, by theorem 6, I think, theorem 6, the inverse exists, right? Theorem 6, invertibility theorem. Alpha from A to B is invertible if and only if it's both 1 to 1 and onto. All right, so if it's also onto, then I can use theorem 6. I mean, also, what I'm about to write, you'll see you could easily modify my argument for this case. I just want to break into two cases. The one case I'm basically relegating to theorem 6. So if alpha of A equals B, then it's a bijection. Therefore, there exists, beta, which is alpha inverse with beta alpha equals to 1A, right? I mean, you also have alpha beta is equal to 1B, right? But anyway, okay. We don't have that for this problem in general, though, because we're not given that alpha is a surjection. That's one case here. Otherwise, there exists B naught in B minus alpha of A, right? In other words, there's a point outside the range of alpha. Okay? Thus, define beta of x equal to, well, let me say beta of y. I'll use y for reasons that'll become clear in just a second here. Beta of y. What am I going to define it to be? I'm just going to let it be B naught for y, which is not an element in alpha of A. All right? And then I'm going to let the beta of y, I'm going to let it equal to, I'm going to let it be bx, where alpha of x equals to y, and of course y is an element of what? Alpha of A. There might be a more clear way to write that. What I'm saying is there's two cases. Either y is in the range or y is not in the range. If y is in the range, we can define it to be the point which maps to y. That's the output. Now, why is that a function? Right. So I mean, if y is outside the range of alpha, it's single valued. It takes a single value b naught. We pick that point. If y is in the range of alpha, it's defined to be x such that alpha of x is equal to y. Like, why can't there be two x's? Well, suppose that alpha of x is equal to y and alpha of x prime is equal to y. What are we assuming about alpha? It's 1 to 1. Right? So that's why this function so constructed is in fact a function. So beta is a function, is single valued since alpha of x equal to alpha of x prime implies x equals to x prime. Right? So that implies that our rule, when y is in the range, gives me a single output, namely the input, which got to y. Yep.
So, are we doing that for any point that exists outside of that, or for any v naught, or are you just?
Yeah, I'm just saying the whole range. I'm mapping to that one constant. I mean, the whole. Say this. Is my point in the wrong space? Where's beta supposed to map to? I may have the wrong. Oh, I'm sorry. That shouldn't be. That's wrong. I'm sorry. You're right, Tim. We want. What do we want? Beta is supposed to go from where to where? B to A, right? So I shouldn't put B naught here, right? What should I put? Right. What's A naught? Right. Which we know exists because A is non-empty, right? A is given to be non-empty, so there's a point in it. That's why you need non-empty. Well, I don't know. Maybe that's just to keep it from getting too pathological. There, now it makes sense. Sorry, I should actually define the function going to where it's supposed to go, namely A. Certainly, this is in the domain of alpha, which is an A, right? And you see that this argument, this function I'm constructing, would just as well be, this is still good, in fact, if alpha of A is equal to B. Like, we could take that case still being covered by this construction. If you look at it, there's really no reason for me to separate off that other case logically. I mean, you could just do you could do both cases at once here, if you're courageous. I separated them because I think it makes it easier for you guys to think about, you know. Okay, so there's beta, and that's a function. Is beta alpha 1A? What is beta of alpha of x? So this is y, right? Alpha of x is y. What's it mapped to? By construction, this is equal to x for each x and a. So therefore, beta alpha is 1a.
Outside of A in the first place, then we would be going back to A anyway.
Yeah. Yeah, so you could pretty much make, but the thing is, we do need to address the possibility, right? Because this beta is a mapping from B to A. So, we have to do something with the points that are outside the range of alpha in principle. We're not given that alpha is onto. So you got to do something with those points. But that's easy. Just throw them to a point. Just pick a point. Stick them all there. Yeah. And of course, this beta becomes the inverse in the case that alpha is actually is surjective. This actually is the construction of the inverse. Right? Now, B implies C is much easier, I think. Right? So suppose, we're supposing, so there exists beta such that beta alpha is 1A, right? And you're also supposing what? You're supposing that you've got, I'll just get straight to the point here, we're almost out of time. Alpha gamma equals alpha delta, right? So just operate by beta. Use associativity of maps. I think I told somebody in the class this was more complicated than that when we were talking about it because I wasn't writing and I was just talking and I convinced myself of something. B implies C is actually pretty easy. C implies A, that I had to think about a little bit. There again, I think you're going to have to invent some maps. I think C implies A is about as, I think C implies A is actually the hardest part of this problem. You got to, because you got to come up with, maps, so I'll help you out with that. So what are you're trying to show alphas 1 to 1, right? That's the goal. Suppose C is true, try to show alphas 1 to 1. So what do? And then we assume alpha of x equals to alpha of y, right? Our goal is to show x equals to y. If we can do that, we've shown that alpha is 1 to 1. I am given that C is true. So in order to use C, I have to come up with maps gamma and delta, right? Which somehow involve these points x and y. Where are the points x and y? They're in A, right? So you guys tell me. Gamma of C equals to blank. Delta of C equals to blank gives alpha of gamma of C equal to alpha of delta of C for all C in C. What can I fill in the blanks with to make this so? There's really only one choice. Fine, there are two choices. I think this is hard because you got to invent some maps to make this go. I mean, you actually have to invent functions, create functions. Don't look down on constant functions. Constant functions are useful. Yeah. See, if I put x there and I put y, in other words, gamma is the function which maps all of c to x, it's the constant function, and maps all of c to y, the constant function, then this is x and this is y. We're assuming alpha of x is equal to alpha y. Check. Then that implies what? Gamma equal delta. But what's that say? That's maps gamma equals delta, right? Pick any c you like. We have x equals y, which shows 1 to 1. This did not come to me as fast as I shared it with you. The only reason I can tell you this in the time we have is because I've thought about this before. It took me some time to think of this. So you should be thankful to your peers who asked me questions about it before. So yeah. Anyway, I'm sorry, I'm going over. If I go too late, I'm going to get in trouble with the home office. So best be going.